Hi, good morning everyone. Thanks for stopping by to watch my talk today. And today we're going to be talking about accelerating Python with FPGAs. And I think this is a very exciting area. A lot of things, I think it's an opportunity. It's a fusion of software and hardware, and I think there's a middle ground here that there's some real opportunity to make some things better here. So I'm going to kind of in this talk today, I'm going to kind of just talk about the hardware and the software, and I'm also going to talk a little bit about the current state of methodologies as to how you can have the software use that hardware. So let's get started. The first thing I want to talk about is I'm assuming most people in here are software people and have never used an FPGA before, and or maybe you are a software person and you know of an FPGA, but you don't know a whole lot about it. If you do know FPGAs really well, this talk isn't really for you, and you probably won't be here anyway. So, what is an FPGA? Well, actually, it's not complicated, but it has a lot of features. We could spend a whole separate talk going into much deeper levels and still not talk about all the things we do. So I'm taking a very high-level approach here. And so my approach here is going to be based around an almost cartoonish version of FPGA, but the parts and pieces that the cartoon shows are very relevant. So let me begin. Here's the actual chip. This is the actual top cover of the chip that's on the Ultra96 board. And underneath that lid is a silicon chip, and the silicon chip is FPGA, but look over here in this diagram. So this diagram is showing some fundamental pieces here. And the fundamental pieces, let's start on the outside and work in. The fundamental pieces are what I/O cells. So the I/O cell is attached to the silicon chip, and the I/O cell actually gets attached to a pin. So FPGAs have a lot of pins, a lot of I/O pins, and one of the differences between an FPGA and a CPU is the functionality of the pins are not defined, they're user definable. So you have a lot of pins, hundreds of pins, hundreds and hundreds of pins on a lot of the mid-grade devices. So you have the I/O cells or pins, and then those pins are connected to this blue track here, and that blue track are called interconnects. And the interconnects are basically just interconnections allowing for these logic blocks to be connected to not only the pins, but to also be connected to other logic blocks. So what are the logic blocks? The logic blocks are predefined piece of hardware. It's more than just transistors. What's in the logic block are little primitives. So an analogy to software might be a assembly language instruction that a CPU runs. It's kind of an atomic, fundamental little primitive. And when you write a software program, you don't just execute one instruction. You actually execute multiple instructions to have it do what you want to do. So these logic blocks themselves are sort of like assembly language instructions, and they can be used together with the other logic blocks through the interconnect. The interconnect allows them to exchange information, just exchange control. So when you write a program for an FPGA, the compiler actually will go and take your source code and wire up these logic blocks and do some setup of these logic blocks, and through the interconnection and the setup will actually solve your problem. It will be kind of the program and execute the functionality that you wanted it to do. So keep that in mind. Again, it's a simplification, but it has relevance. So a little more detail about the logic block. So the logic blocks themselves, Xilinx has looked at what people want to do with this, and similar to an assembly language instruction, the CPU makers have decided, well, if we have a certain number of these types of instructions, these are really useful to people and they get the job done well. There's always some trade-offs, so you can't solve every problem. So the analogy is still the same with these logic blocks, and the idea is that like Xilinx is taking a look at the problems people are trying to solve and saying, well, if we make this kind of fundamental primitive, this is really useful. One of the most useful pieces when it comes to doing signal processing, machine learning, and image processing are these, what they're called DSP slices. And the Ultra96's part actually has 360 of these parts and pieces. And in the piece, again, oversimplification, but really one of the major features of this DSP slice is to perform a multiply accumulate. So it has hardware multipliers and accumulator and can really quickly do a fixed point multiplication and accumulate. And there are some additional features in there, all kind of DSP math oriented, okay? And there's some other parts that are in here, and there's a little diagram of some of these parts and pieces. And I think the important takeaway is just to, like I said, think of them as primitives, really useful primitives. And these primitives are actually they are inside the logic block parts of the FPGA. So here's actually the inside of the FPGA chip. Here's the actual picture of the silicon die itself. And just to give you a little frame of reference, they have hundreds of thousands of these little primitives in them. And here's a little just analogy, but here's a DSP slice and arrow pointing to this tiniest little spot. You know, it's not like this thing takes up a whole lot of space. There's just a whole lot of them and a whole lot of other pieces. And one piece I didn't mention is also in the FPGA has memory inside. So so a real quick functionality, if you can combine the logic with the memory, and you can build state machinery. And if you can build state machinery, well, then you can really solve any kind of problem. Over to the right of that part is actually a compiler output. So this is not a chip. This is, you write your source code, the compiler synthesizes it, and then does what's called a place and route. This is actually a diagram, kind of a summary. There isn't really a direct analogy back to the software world. But it's kind of like a linker map in that what it's showing is it's showing you the resources that your program used from the FPGA. So that's what that is. Where it's highlighted here, it's actually using one of those little primitives inside and the interconnects between them, or how it's all connected. And where it's dark, there are primitives and interconnects, but they're not being used. So you can still see this program, and this, by the way, is an output from an Ultra96 part. This program actually just used about this much of the part, and all this is still unused. All right, so why would I want to use hardware? I think it's a fundamental question, and there's a lot of really good things you can do with hardware, but I would say the best one answer, if you had to pick just one, is speed. The speed comes from a lot of different things, but primarily the speed comes because, remember, these logic blocks, there's multiple ones. It can execute parallelism. So all those logic blocks that you saw in there can independently at the same time perform functionality. And that's fundamentally where the speed up comes from. Some of the speed up also comes from some of those little primitives themselves having that hardware, hard-coded hardware that can get the end result in a really short amount of time. All right. So another thing I'd like to mention about why it's useful for hardware is another really strong attribute is that the FPGA, being a piece of hardware itself, can be very deterministic. Meaning if I want to have the hardware perform something and I want to count on it being done and I want to have consistency, it means amount of execution time. FPGA can be very deterministic. Its jitter and execution can be in the picosecond range. You can't achieve that kind of determinism when you're running on a CPU that has cache, that has pipelines, that has running on an operating system and servicing interrupts and all that kind of stuff. You just can't get that kind of determinism. So a common usage for the hardware is you write your program for the things that you can afford to you don't have to worry about your execution time, and the things that are critical, you can hand it off the hardware. So that's another real strong area where the FPGA can assist software. There's a whole bunch of application areas where FPGAs excel. I can't think of one area where you couldn't use it. There are some areas where it does make sense for a CPU to do the job, but FPGA could still do it. And then there are a lot of other areas where FPGAs are just better to use from the perspective of being faster, in some cases lower power consumption, or even be able to do things that you just couldn't do at all with a CPU or even a couple CPUs. There's a long list here. I'm not going to go through them. You can take a look yourself. Okay. So I do want to make go just into detail and provide one example of many that could be provided about that speed increase. So if you stop by this afternoon, our bench out front there on the monitor, we're running this actual demo. But the real quick summary is, with the hardware assist of the FPGA, the demo, it's an image classification. It looks for road signs. With the hardware at full 1080p, we're able to do 66 frames per second. Without the hardware, just the software, running on the same Ultra96, so running on the ARM cores that are on the Ultra96, that software was only able to achieve 0.01. So that's a factor of 6,000 speed up. So that's quite a dramatic difference, and it just gives you a little bit of an idea about how much better the hardware can, how much faster the hardware can execute some algorithms. And the link's provided if you want to go take a look yourself, you can. So one of the things that's about Python, and so now I've talked about FPGA, I'd like to kind of try to get you guys into a context you're very familiar with. I've drawn a diagram here with a dividing line, hardware on the bottom and software, and kind of trying to depict at a very high level the layers of Python related to hardware the way it would be on a typical system. And so here you have your Python source code and some libraries, and then you have the Python interpreter, some kind of Python environment, Python engine that uses libraries itself, maybe that are built with other languages, and then those libraries interface with the operating system, and then you have the operating system and a hardware abstraction layer. There's other variants of this, of course, but I think this is a decent generic kind of way of looking at it, and I think you should probably be pretty familiar with that kind of summary of it. And then on the bottom, the hardware is, you know, your PC, your laptop, CPU, memory, I/O, and that stuff. All right? So I like to take a step back. So we're going to try to add the PL into the system and keep with the framework that you understand. If I have an FPGA, that's a piece of hardware. It's a separate chip. So if I just view them as separate chip, right now, for simplification, you have your PL, and then over here is your CPU. And if you want your CPU to talk to that FPGA, you have to have some kind of data bus between them. So in the beginning, that's the way it worked. I spent years, a long time ago, working on systems where the FPGA was separate. We had a CPU, and we actually had to build our own bus inside of here because the FPGA didn't have a bus built in. So we actually had to design, write source code to design the data bus interface here so the CPU could actually talk to it. Okay. So now, if you add Python today, you're running it all on the CPU. If you want to talk to the PL FPGA, you've got to get your information from Python into the FPGA, okay? And if you run Python, Python itself doesn't really access any peripherals. You typically will, from Python, call into a C library or some other language's library, and then that library is actually interfacing with the hardware. So to interface Python with C, there's a lot of different techniques that people use, CFFI, C-types, Python. There's a lot more. Everybody kind of has a favorite and some reasons for using those different methods to interface Python with C. So if you get from Python to C, then you can kind of get to hardware. So the idea would be if I had FPGA, and then I built my hardware bus here, and I could call Python, and I could have some device drivers, some C code. I call them from Python, then I could exchange information with the FPGA. All right. Well, you don't have to quite work that hard, because in the Ultra96, what Xilinx did is they took two separate parts, the FPGA and the CPU, and they put them all in one chip. And that's the ZU3EG chip that's in the Ultra96. It's called a Zinc part, which is a system on a chip. So here's an overall block diagram of a system on a chip. And if you're familiar with software, you're very familiar with this part of it. The terminology is processing system, not CPU, actually. And so the short notation for that is PS. And instead of FPGA, it's actually called programmable logic, or PL for short. So if you have a PS plus a PL, you have an MP SoC Zinc. And there's ARM cores here. There's actually 4 A53s in the Ultra96, and then there are 2 real-time processors in addition. There's memory controllers, there's peripherals. These are all features in the Ultra96 board. And then down here, you have the programmable logic, and there's the DSP slices and the memories and the pins, and there's some additional functionality transceivers. This is a superset, so the Ultra96 doesn't have exactly every feature. Xilinx's different parts have different amounts of functionality. This is a general purpose overall showing all the features across from the least to the most feature oriented part. All right, so talked about kind of the hardware. Now I'd like to shift to talk a little bit about the compilers. So if you write source code on a CPU, you take your source code, you compile it, you get a binary, you run it. The hardware has the same analogy. You have source code, you compile it, and you run it per se. But their tools are not called C compilers or C++ compilers. The tools, there's a couple of them that do slightly different things. The most used tool or most functional but doesn't do everything for you is called Vivado. And Vivado is a GUI-oriented tool. It also has command line capability, so it's suitable for production environment development as well. And it does a lot of things. Not only does it take programming source code and kind of compile it, it also can help you manage the resources. It's the tool that generated that little place and route. It does a lot of things particular to FPGAs. And again, it's kind of the main tool. So let me talk about a couple more tools. There's just a picture here where you have the source code going in. It's just trying to show you again, put source code in and compile, and you get the binary out. And the binary for the FPGA, the executable, used to be called a bit stream. Okay, a bit stream is the same version, is very similar to a .exe or a .bin running on a CPU. There's some additional terminology when you go to use the PYNQ framework, which we'll talk about in a second. They actually call it an overlay. Right? So another tool is HLS, and just real quick, I got to speed up here a little bit. HLS is a tool where you can write in C and C++. There are other languages that in the past that people used to program the FPGA, but you can use HLS and you can take C, C++ code and then compile executables for FPGA. That wasn't how it began. There are other languages, again, VHDL, Verilog, you probably have heard of those, maybe aware of them, that are different than C, but this tool allows you to actually take C and program the FPGA. And I don't mean program as a linker loads a binary into the part to program it. I mean actually create and design the hardware using C, C++. The other tool that's real popular, and my colleague Dan Roswood, later on today, I think around 5 o'clock or so, he has a talk, goes into a lot more detail. And Adam Taylor later on in the day also will talk about SD-SoC. SD-SoC is a tool. So here's the key why I broke up the diagram, the two separate parts. This tool not only will allow you to design hardware writing in C, C++, but this tool will also move the data for you from the CPU to the FPGA. So if you use this tool and you write in C++ from your Python, if you can call into C, C++ from Python, then you do a call and this tool generates code and some hardware itself to actually move the data from the CPU over to the FPGA. This SDK tool, all of you I think pretty much know what this one, you might not be familiar with the name. This is actually an Eclipse-based development debugger tool for actually programming and developing on the CPUs itself. Remember the PS part. So this primarily functions with the PS part. So you've got Vivado, you've got HLS. HLS generates hardware, but HLS, I didn't say it doesn't move the data. Then you have SD-SoC that moves the data, can generate hardware. That's all for the PL. And then you have XSDK for the PS, to use the PS portion of the Ultra96 part. Now, finally, there is an operating system, Linux operating system, that's called PetaLinux. It's an open source, it's embedded Linux, and underneath the hood, it's actually a Yocto-based build system. It's a 64-bit ARM architecture, embedded Linux. I don't want to spend any more time talking about that right now or in this talk, but that's another important tool to the mix here. If you're going to run Python, you can run Python on top of the PetaLinux OS. So here's actually, now I'm going to go back to that diagram, change a little bit. I've now added in, you notice at the bottom, the FPGA portion, which is just like, it's just an add-on to the hardware. It's another piece of hardware that gets added on, it's inside the chip, it's on the Ultra96 board, and you have a HAL, PetaLinux, all the rest is the same. And so with the colors here, what I'm trying to show is that if you want to actually have your Python use the FPGA or the PL, these are the areas that you're going to have to change. And I've got a mid-grade here. Depending upon how you do it, you may also have to touch these layers of the system in order for your Python source code to be able to use some functionality that you've designed into the programmable hardware. All right. So there is another framework that's new. This is going to be released in the first week of October called PYNQ. And PYNQ stands for Python for Zinc. And it's a framework. So this framework will help you if you want to have Python be accelerated with hardware. This is a nice little set of tools that will help you, that will make that easier for you if you fit within some of the little constraints that it provides, which are very light. So some of the features that it gives you, it's a library. It's a little bit more than a library. It's also implies it's going to have an Ubuntu file system, and it's going to have Jupyter Notebooks installed. So there's some application level things that come with a PYNQ kind of setup for Ultra96. But fundamentally, it's a Python library, and in that library, it's going to provide your Python code the ability to get interrupts from hardware and manipulate some of those FPGA pins. It allows you to do some memory mapping. There's some shared memory that the hardware can have access to, that your user space application to. There's some helper functionality here. There's the overlay, and again, I mentioned that is the same thing as the EXE for CPU. It's a little different, but just you can think of it that way, for now. That's a good enough analogy. Bitstream used to be the old terminology. If you're using PYNQ, it's overlay. So overlay means I call a function to load my bitstream, my EXE, my FPGA program. I give it the file name of the program, and this function handles loading the program into the FPGA and starts it up and runs it. There's a few other features that get some attributes about Zinc into Python. There's a little bit of acceleration of NumPy in there, actually, and a few other little things. So I provided the link, and you should definitely go take a look at this, and it'll go a lot more detail, and it'll make, I think, a lot more sense than just listen to me. But just take that point away from it. Go to have a look at those instructions, and I think you'll see a lot of things that will be useful to you. Okay, so now let's take the diagram and put it into the context of PYNQ. So really, what PYNQ, remember I said it helps you. So remember the diagram, you have your PL stuff here, and you have your source code here, and you want your source code to be able to use the stuff that's in here. Well, PYNQ has already modified these layers for you. You don't have to touch them. Really, all you have to do if you're going to use PYNQ, if you want to accelerate Python with hardware, is you just touch the endpoints. You touch your source code. PYNQ will help move your data from your source code into the programmable logic, and the programmable logic can do the acceleration, whatever chore you're trying to accomplish. All right. So I know this is like a whole lot of information. There's just a lot of things I just talked about. It didn't go into great detail. I can't emphasize there isn't anything more important. If you're interested, go take a look at the pynq.io community, because on that website are videos, designs that people have already worked out, and I can't do anywhere close to as good a job sitting here trying to explain to you with my hands and a few slides of how to use this thing. The best thing you can do, if you take one thing from this little talk, is go take a look at this website yourself, do a little reading, watch some of the videos, and it's going to help you a tremendous amount. This should quickly be able to get you to the point of being able to actually utilize this system and to accelerate some of your own programs or own functionality using the hardware. There's some other examples, tutorials, but also people have actually done designs, and they put their finished designs on this website, and the majority of them, all of them are open source. So they left behind all the source code, all the tools, the make files, and there's some really neat demos that they have up there, machine learning and robotics, and there's signal processing things, video processing things, hardware control things. It's all up there. Really, go take a look. Again, that's the most important thing that I could stand here and tell you to do, and the most important thing for you to do would be to actually go take a look. Okay, so I mentioned first week of October, we're going to actually be hosting on our GitHub the files necessary for the Ultra96 that integrate in with this PYNQ framework. So keep your eye on that. First week of October, it should be showing up. Okay, so let me try to summarize all this. Let me try to summarize a whole bunch of stuff, compress it all down into one slide. What I've tried to create is a very high-level kind of flowchart approach to this. If you start off at the top, okay, the first thing you have to decide is what do you want the hardware to do for you? What thing do you need the hardware to accelerate or the job to do? Decide that. Okay, that's your first step. Now you have choices. And I mentioned in the old days we had VHDL and Verilog, and you can still use those. And if you have a hardware person who knows those languages and how to do FPGAs, that's still a very valid and relevant path. So you have a path of doing VHDL Verilog. Now if you don't have a hardware person, you don't have someone with all that experience, the other alternative path, and especially if you're a software person, this is new to you and you want to get going, the other path is to take your algorithm in C or C++ and use the HLS or the SoC tools. So if you follow along just one path here, so let's go take a look. So decide what you wanted to do. You've got an algorithm in C, and now you want to implement that algorithm in your hardware. You've still got two choices. You can use HLS, and you can use SDSoC. If you use SDSoC, remember what's the difference? Well, it actually moves the data and creates and designs the hardware, so it does those two things. That's going to be the easiest thing for a software person to actually do. So the easiest path is going to be kind of stay all the way on the right of this tree, okay? And then the final block of that tree is how do you want to get, so you have C code, now you've got to get to Python. So now you just need to choose whatever your favorite method is to get from Python to your C code, and you're done. Now you've accelerated your Python using these tools, you're now getting your Python accelerated in hardware. So there's some other in-between, so if you didn't want to use the easiest path for a software person, SDSoC, you still can have C++, use HLS, and then if you do still have access to someone who has hardware knowledge, you can work on moving your own data in your own way and have all the control over it if you want. That's still also a viable path if you want to do that. If you've already got some VHDL from the past, some intellectual property, this is still a relevant path. And then what I've also added in here is how could PYNQ help you? So you don't have to use PYNQ. If you don't want to, you can do it all yourself. But if you want to use PYNQ, I've kind of added in these little PYNQ blocks, the path that you could also use PYNQ to help you get your job done. PYNQ can be used to move that data too as well. So that's kind of why here, for example, VHDL, you've got your hardware programs, but you've got to get your data from Python into your programmable logic. You can have PYNQ get your data from Python, because PYNQ's all Python, and it'll push the data over to the PL. So that again, is a valid path. And you don't have to even choose your method, the interface to C code here, because this Python code, the PYNQ framework already has done that work for you. It's just a Python call, and then you can push it into the PL if you use that framework. So that's a little confusing, and it's one of these things where you kind of have to jump in and do it to really understand it. And I'm trying to provide some guidelines here that I hope you find useful. And so that's about all I can say in this short amount of time. Here's if you don't have an Ultra96 board, here's the URL to get one. They're $250. You buy them from Avnet. I wish I had one of these a long time ago. It's $250, but it's really a lot for what you're paying, especially all that functionality in that Zinc part, and it has the 96 boards, connectors on interface on it, display port, you can drive a monitor, USB 3.0, it's just got a Wi-Fi chip, it's got a whole bunch of things in it. So it's really going to be a really fun board to use. It's really capable of a lot of machine learning stuff and signal processing. It's really a really fun board. And that's really all I have to say. I'd just like to thank everyone for taking the time to come out and watch my presentation. Hopefully I made some sense to you. Please stop by and ask me questions if you have them. Thanks again.